Okay, so this video focuses on wireless attacks. We have wireless technologies over here like Bluetooth, infrared, Wi-Fi, and a lot more. So what happens when most of the attacks like infrared is the data is completely unencrypted. So there is a word encryption. Let's dig into encryption and see how it works. So suppose we have a word over here. It goes through some encryptive function, say shift 3, and produces a completely new garbage. So coding liquids changes to something like FRGLQJ. How it converts to this garbage depends on the key over here, provided shift 3. So you can see C plus 3, that is DEF, it became F, O plus 3 became R, and D plus 3 EFG, it became G. So that's how you can find out the entire encrypted word of this real plain text. What if you want to decrypt the text? If you know the encryption key was 3, you can easily decrypt the text by going 3 digits back. So you can say unshift 3. So here key is a very important part. But you can see that shift 3 is really weak encryption. There are only 26 possible shifts because of 26 possible alphabets. So this is really weak, and as you might remember from brute force, that this can really easily be brute forced. There comes one more encryption called RSA encryption. This encryption is currently in use, and this encryption provides two keys, one for encryption and one for decryption. Though both the keys are different. So one thing common in all the encryptions is you need to have certain key to encrypt or decrypt a message. So keys are really important and they should be kept somewhere safe and secret. So what is the problem with all ciphers? So encryption are also called ciphers. You can usually use them whatever you like. Ciphers, encryption is all the same. Problem with shift ciphers is they are really easily brute forceable. There are only 26 shift values possible because there are only 26 alphabets possible. So let's go to substitution ciphers. This depends. This works like a letter A is substituted for a letter say B, and a letter B is substituted for Z, a letter C is substituted for F. So there's entire different substitution for every letter in the alphabet. So basically in this substitution cipher there would be 26 factorial shift values possible. So this is a really huge set, and this could be a good cipher, could have been a good cipher, but there is an attack called frequency attack. In any English paragraph, you can see that the letter E occurs the most number of times, followed by certain letters, say D, then A, then O, as you can see over here. And letter Z appears the least times. So using this English letter frequency, you can really easily decrypt a message that has been written via the substitution cipher. So you can say, yeah, if a single character is being replaced by one single different character, that's really easy to crack. Now, we know what encryption is. Let's go into Wi-Fi protocols. There are mainly three types of Wi-Fi protocols. One is WEP. It is outdated. You might have seen it somewhere, but it's really outdated, vulnerable, not in use. This is, yes, easy to hack. You can search about it, how to hack, but as it is outdated, we won't be considering this one. Let's go to WPA and WPA2. WPA2 is most popular out there. Whenever you create a new hotspot from your mobile phone, what you are creating is a WPA2 network. So this is the most popular one over there. And the last one is open, where you don't set any password. So here I will stop you and tell you what password over here really is. Whenever you set a password in your Wi-Fi network, this is the key for the encryption. So here shift 3 or say RSA K1, this is your password, that whatever you are entering in your Wi-Fi access point or the Wi-Fi station. And the data over here, the coding liquids, this is your HTTP request. Everything, say you are opening a site xyz.com, maybe codingliquids.com, whatever site you are opening, that site names and the data you're sending to and fro from the site, Everything is this real text, plain text data that goes through the password, the Wi-Fi password, and that changes into something really different from what the real data is. So that if two or three guys are connected on the same network, they can't see what each other are browsing. This is really necessary. But what happens in open networks? Everyone can see what other person is browsing. So open networks is kind of insecure. So let's see how WPA2 connection establishes itself. So before getting any connection, as you might guess, that the access point and the station, that is the access point which is broadcasting the Wi-Fi network, and the station is the device that is connecting to the Wi-Fi network, both should know the key, right? Here, if I am sending you this weird text FRGL, you should know that the key is 3 to decrypt it. So if you're the station, you should know the key. And if this is the access point, this is the Wi-Fi network, they should know the key is 3 so that it can encrypt it. So you must need to know the key. So what happens is a PA2 handshake between access point and the station. So they send certain data to and forth, certain data goes and comes around. They're able to find out that the access point in the station is having the exact same key, right? Because the access point, the router, say the router, it is broadcasting a Wi-Fi network and it is having certain key and it needs to authenticate that you are having the same key as well. So it exchanges certain data and then finds out, yeah, you're having the same key. And yes, they never send the same key on the network. So even if you're able to read this data, or entire this conversation, the WPA2 handshake, you would not be able to know what the key was. This is really magical, isn't it? You can see what was there, but you can't see what the key was there, what was being transmitted. Let's see how this works. So suppose I'll be considering a really simple example. So what happens is, suppose I have a text called HRITIK. So there is a special command called MD5 sum. So basically this generates certain hash. Let me just explain quickly what this means. So if I'm generating MD5 sum of coding liquids, and here I go. I get this weird long text 3B6F. This is really nonsensical. But what there is certain that every time I generate the text coding liquids, it is certain that I will get the same text here and here. I'll be getting the same text every time. It doesn't matter if I'm calculating this from my computer or your computer or any computer in the world. As long as I'm using MD5, it's gonna give me the same result. But it's really tough to reverse this. So you cannot use this hash and find out the real plain text was coding liquids. So this is really exciting. This is a one-way function. It's similar to how you can multiply two numbers together, say 13 and 3, it becomes 39, right? But the multiplication was really easy. Multiply 3 to 3, you get 9, 3 to 1, you get 3, and it became 39. But when you are said to factorize 39, you'll have to try with 1, 2, 3, 4, 5, and until you reach the digits 13 and 3. So yeah, this is a one-way function. Going from the plain text to MD5 hash is really easy, but reverting the entire thing is really tough. You need to try all the possibilities. So if I want to change, if I want to find out what is the reverse of this hash, I'll have to do something like say C. Let's find the hash of C. The hash of C is a long different completely different set of string. Let's find for CO. It's again completely different. You can see they are completely different. And slowly if I go to coding liquid and I see it's again completely different. 3E79 coding liquids by 3B6F and something else. So it's completely different. until and unless I reach the exact same plain text that was coding liquids. Until and unless I get reach this exact same plain text, I won't be able to find out what was the meaning of the hash. So yeah, to get the meaning of this hash, to get the real text of this hash, I need to try out all the possibilities. So hashing is a one-way function. So what they do over here is they exchange hashes of their Wi-Fi password. So this is the entire method of generating hashes. This is really complicated. You can get into it later on. But they somehow exchange certain hashes so that access pointers show that yeah, they're having the same password that is configured for the Wi-Fi network. And then the connection is established. After this, the key has been exchanged. This was a real important stuff. The key has been exchanged, and every connection is going to be encrypted with the key that has been exchanged, right? So let's hack this one. So all the data after the handshake is encrypted with certain key, but the handshake isn't. Everything this data is going through the network, just lying around in the network. It is not encrypted at all. Anyone can capture these data, right? But I just told you this is a one-way function. So what can we do? If there is a one-way function, we can always brute force the function. As I told you earlier over here, we can try C, then CO, then COD, then CODING, something like this. And we can go on trying and trying and trying until we find the correct key. So what's the catch here? Is if we are able to get all these data, all the handshake data, we can store it on a certain machine, some other machine that is really, really fast. It doesn't need to be connected to the internet, doesn't need to be connected to the Wi-Fi network at all. It just need to contain this important data, and then we can try the brute force attack on this handshake. So let's try this on.